showcasing groundbreaking mega-bridge projects where advanced engineering, bold architecture, and large-scale construction converge to reshape landscapes and connect communities worldwide. The Padma Bridge is a landmark multi-purpose road-rail structure built across the Padma River, the main distributary of the Ganges in Bangladesh. Connecting Lohajang in Munshiganj with Zazira in Shariatpur and part of Shibchar in Madaripur, it links the underdeveloped southwest to the nation's northern and eastern regions. Inaugurated on the 25th of June, 2022, it is regarded as the most challenging construction project in Bangladesh's history. The steel truss bridge features a 4-lane highway above and a single-track railway below, stretching 6.15 kilometers with 41 long spans and supported by 42 pillars with deep piles. It is the longest bridge in the country. Construction was divided into major components, involving Chinese and Bangladeshi contractors for the bridge, river training, and link roads. The construction of the Padma Bridge represents the realization of one of Bangladesh's greatest national dreams. Spanning the country's widest and most unpredictable river, this multi-purpose bridge stands as an icon of self-reliance and confidence for millions. Both riverbanks have become vibrant hubs of activity as the project's 5 major components, main bridge, river training, Mawa Approach Road, Janjira Approach Road, and 2 service areas advanced rapidly after work orders were issued in late 2014. Construction on the river is highly intensive. Floating cranes, giant hammers, and heavy barges dominate the scene as 120-meter steel piles, fabricated from 60-millimeter plates, are driven deep into the riverbed. The German hydraulic hammer, capable of exerting 500 tons of pressure, ensures stable foundations in one of the world's most challenging geological environments. Test piling began in March 2015, and following its successful completion, the main piling works were inaugurated by Prime Minister Sheikh Hasina. China Major Bridge Engineering Company leads the main bridge construction, employing massive equipment including 1,000-ton floating cranes. A total of 42 piers and 41 steel truss spans will form the 6.15-kilometer structure. Meanwhile, river training, considered the most technically demanding task due to the Padma's unpredictable Amazon-like behavior, is undertaken by Sino Hydro Corporation. Over 13 million concrete blocks and millions of tons of stone and sand are used to protect 14 kilometers of vulnerable riverbank. Three modern service areas have been developed, including residential units, utilities, and recreational facilities. Approach road construction, carried out by Abdul Monem Limited in partnership with Malaysian company HCM, connects the bridge seamlessly to the national highway network. The government also acquired more than 200 hectares of land, establishing 8 resettlement centers to rehabilitate affected families, and planting nearly 400,000 trees to restore the environment. Supervised by the Bangladesh Army and Korea Expressway Corporation, the Padma Bridge is expected to boost national GDP by at least 1.2% annually. As the project nears completion, a proud national dream is steadily becoming reality. The Tobolsk 2 project represents one of the most ambitious petrochemical logistics operations in northern Eurasia. Its first major milestone begins with the MV Happy Sky, en route to the remote port of Kirkenes, Norway. This marks the end of a 50-day, 12,000 nautical mile journey that started in Onsan, South Korea, where the vessel loaded 5 massive heavy-lift columns for the ethylene cracker unit under construction in Tobolsk, Russia. Supplied by Linda Engineering, these columns will form the core of a world-class petrochemical complex designed to produce ethylene, propylene, and butadiene, key building blocks for global plastics manufacturing. The shipment aboard Happy Sky alone amounted to nearly 30,000 freight tons, with the largest unit weighing 917 tons. In total, for the Tobolsk 2 project, Dugro transported more than 990,000 freight tons of oversized and heavy equipment across 6 major voyages. This effort required the chartering and mobilization of 4 specialized seagoing barges, each capable of carrying individual units exceeding 200 tons through the Amur River system deep into Siberia. Built in 2014, the Happy Sky provided the ideal platform for such demanding operations. With 2 cranes capable of lifting 800 tons and an ice-class 1A hull, the vessel ensured safe handling in harsh northern conditions. After arriving in Kirkenes, Dugro executed a precise transshipment onto barges despite the constraints of the narrow old iron ore pier. Following weeks of river navigation through remote Russian terrain, the cargo finally reached Tobolsk, where Linde Engineering received the critical components. The project showcases Dugro's expertise in solving complex logistical challenges and supporting major energy developments across the Northern Sea route. The Amur gas processing plant is one of Russia's largest and most strategically significant energy infrastructure projects, designed to process natural gas delivered through the Power of Siberia pipeline. By April 2021, overall construction progress had reached 75.1%, marking a major milestone in transforming the site into a fully integrated gas processing hub. A key achievement at this stage was the complete connection of the plant to the Power of Siberia main gas pipeline, with all 4 tie-ins for commercial and feed gas lines successfully finished. This enabled the commercial metering stations to finalize preparation for gas supply, while area improvements continued. Across the plant, multiple technological units advanced into commissioning. The feed gas dehydration and treatment unit began receiving feed gas, and teams worked on configuring the equipment sequence diagram. At the booster compressor stations, the GPA Ladoga 1 unit was fully prepared for gas supply and hot start, whereas GPA Ladoga 2 proceeded through alignment and cold start operations. The ethane, NGL, and nitrogen-helium mix unit also approached the commissioning phase, with preparations for dehydrated gas supply nearing completion. Meanwhile, the central operator room, the heart of plant-wide control, progressed with final finishing works and landscaping, and functional testing was conducted for the equipment of Process Line 1. Significant progress was also made at Tank Farm 3, where the first spherical tanks became ready to receive and store LPG. The operator room and the fire extinguishing pumping station in the feed and product area were similarly completed. At the nitrogen and air station, air supply to the mains was established, and nitrogen supply preparations were underway. Supporting facilities advanced steadily as well. The water treatment plant moved from installation to commissioning, and priority structures of the sewage treatment system were completed. Finally, the power supply building was handed over for operation, providing workspace for 286 operational personnel. The Fisher prototype concrete wall project demonstrates an innovative cast-in-place system developed as an ideal solution for the U.S. Customs and Border Patrol's border wall program. This patent-pending method was showcased during construction of a full-scale proof-of-concept wall at the U.S.-Mexico border in San Diego, California. The process emphasizes safety, speed, and consistency, enabling Fisher to meet or exceed all required technical specifications. Work begins with grading the footing, installing reinforcement, and placing concrete to form a strong base. The following day, vertical and sloped forms, rebar cages, and bulkheads are efficiently assembled to create each wall segment before high-strength concrete is poured. With rapid curing and minimal equipment, the system allows continuous daily progress. The result is a robust, long-lasting concrete wall and a streamlined construction approach ready for large-scale deployment. The Cass Road Bridge project represents a long-awaited infrastructure improvement for Traverse City, marking the first of two major undertakings to replace the outdated one-lane bridge, remove the Boardman Dam, and reroute the Boardman River. For decades, residents had relied on the narrow road that crossed directly over the dam, a configuration that often created bottlenecks and lengthy queues during peak hours. When Grand Traverse County announced in 2007 that the dam would eventually be removed, the possibility of a modern two-lane bridge promised safer travel and faster, more reliable traffic movement. Yet it would take nearly 10 years of planning, permitting, and coordination for the new crossing to finally move forward. One of the defining challenges of the project was the location. A swampland corridor with a high water table that required 22,000 cubic yards of excavation. This demanding terrain, combined with the need to detour traffic for 5 full months, placed significant pressure on the construction teams. Another unexpected challenge involved public communication. Because the new bridge had to be completed before the dam's removal, and before the new river channel was excavated, many residents struggled to understand why a bridge was being built over an area that appeared to be dry land. To address these complexities, the construction teams adopted a collaborative approach. Working as a subcontractor to general contractor Davis Construction, Team Elmers coordinated closely with fellow subcontractors and Grand Traverse County officials. Together, they mapped out how the landscape would change once the dam and existing bridge were removed, ensuring that the new structure would be appropriately positioned to span the future river channel. At the same time, outreach efforts were made to help the public understand the sequencing of construction and the long-term vision of the project. Team Elmer's role in the field began years earlier, applying for a bridge grant in 2012 that would later fund a significant portion of the work. Actual groundbreaking, however, did not begin until 2016. Once construction started, the crews pushed ahead at full speed to avoid delays. Major structural components included 15 concrete and steel deck beams, the largest stretching an impressive 134.5 feet. Each beam weighed so much that US 31 had to be temporarily closed to transport them safely to the site. After installation, Team Elmers placed 350 cubic yards of MDOTD mixed concrete to form the new bridge deck. Beyond the bridge itself, the project required extensive roadway work. Excavating the old roadbed, installing storm sewers, performing grading and earthwork, building the gravel subbase, and finally paving both the approach road and the bridge surface. Although the completed bridge initially stood over dry ground, its purpose would become clear once the old dam was removed and the new river channel was opened. Ultimately, the new two-lane cast road bridge is designed to handle up to 15,000 vehicles per day, a dramatic increase from the 500 daily vehicles previously constrained by the one-lane structure. This upgrade marks a transformative improvement for mobility, safety, and regional connectivity in Traverse City. The construction process for the replacement of Dickinson's Creek Bridge began with the development of a temporary detour route. A detour road and a modular steel bridge were constructed adjacent to the existing structure to maintain traffic flow during the replacement. The detour bridge was assembled using prefabricated components and launched with cranes and temporary supports. Utilities were also relocated to ensure uninterrupted service during construction. Once the detour was operational, demolition of the old bridge commenced. Crews removed existing barriers, asphalt surfacing, and deck slabs. Heavy machinery, including excavators with hydraulic breakers, was used to dismantle the concrete superstructure and piers. Debris was loaded onto trucks and transported off-site. The site was then cleared, and erosion control measures such as sediment fences and mats were installed around the creek. Foundational work began with excavation to the required depth on both sides of the creek. Steel reinforcement cages were positioned in excavated pits, followed by the placement of formwork. High-strength concrete was poured to form deep footing pads. Temporary cofferdams and pumps were used to keep the construction site dry during this phase. Next, precast abutments and wing walls were installed and precisely aligned. Once the substructure was completed, large precast concrete girders were delivered to the site and lifted into place using mobile cranes. Each girder was carefully aligned and seated on elastomeric bearings atop the abutments. After girder placement, workers installed reinforcing steel mesh and formwork for the concrete deck. Concrete was then poured in multiple sections to form the bridge deck, which was cured under controlled conditions. The deck surface was then treated with a waterproofing membrane and finished with an asphalt overlay. Subsequently, parapet walls and bridge barriers were cast along the edges of the deck. Expansion joints were installed at each end to accommodate thermal movement. The bridge approaches were backfilled and compacted, followed by paving and the addition of road markings. Final site restoration included removal of the detour bridge, grading of the surrounding area, seeding, and placement of rock armoring along the creek banks to prevent erosion. Drainage systems were also finalized. Before opening, the bridge underwent safety inspections, load testing, and line marking verification. Once certified, the new Dickinson's Creek Bridge was officially open to traffic. The replacement of the rail bridge at Cow Lane in Reading was carried out in two major phases: the offsite construction of the new bridge and the complex operation to relocate and install it in place of the old structure. The new bridge was built in a staging area adjacent to the railway, allowing work to progress without disrupting train services. Engineers assembled the steel framework on solid foundations, carefully aligning sections to ensure accuracy. Reinforcements and crossbeams were added to create a robust structure capable of supporting heavy rail traffic. The deck was installed and secured, forming a complete bridge ready for installation. By preparing the entire structure in advance, the project minimized the time required on the active railway line and ensured efficient execution during the replacement phase. Once the new bridge was fully assembled, attention turned to the removal of the existing structure and installation of the replacement. First, heavy lifting equipment was brought into position, including self-propelled modular transporters. These specialized machines were maneuvered under the new bridge, raising it slightly off its supports. The massive structure was then carefully transported along a prepared route toward the railway corridor. Precision control was essential as the bridge, weighing hundreds of tons, was moved slowly into alignment with its final position. Meanwhile, the old bridge was dismantled and lifted out, clearing the site for the new installation. After the existing structure was removed, the new bridge was rolled into place and carefully lowered onto prepared abutments. Engineers conducted precise adjustments to ensure a perfect fit and secure seating. Once in position, the bridge was locked down, and final connections were made to integrate it with the rail line. This coordinated effort allowed the replacement to be completed within a limited time frame, minimizing disruption to rail services and ensuring the new bridge was ready for operation. During the Christmas period of 2011, a significant rail bridge replacement project was carried out at Cow Lane in Reading. The new 600-ton concrete and steel bridge had been constructed in advance at a nearby site to minimize disruption. On Christmas Day, the old bridge was demolished using heavy machinery, including excavators and hydraulic breakers. Debris was quickly cleared to prepare the site for the new installation. Initial groundworks followed, including excavation and preparation of the foundation area. However, water infiltration into the foundations caused a delay, requiring additional drainage measures before proceeding. Once the foundation was stabilized, the installation phase resumed. On Tuesday morning, the new bridge structure was transported to the site using a 66-axle self-propelled modular transporter. The massive vehicle moved slowly and carefully, guided by engineers and spotters to ensure precise alignment. The entire maneuver took approximately 7 hours and drew attention from local residents who gathered to observe the operation. Upon arrival at the final position, the bridge was lowered into place onto the prepared abutments with high precision. Workers then began securing the bridge and making structural connections. Following this, crews started installing new railway tracks over the bridge deck. The new bridge was designed to increase the clearance under the structure, allowing for future road widening. After the bridge was installed, construction teams worked beneath it to adjust road levels and prepare for the addition of 2 traffic lanes, a cycle lane, and a pedestrian footpath. Using SPMTs lanzadora de traves, the assembly of